Okay, in this video we're going to be talking about discrete random variables. And so here are some of our objectives. We're going to distinguish between discrete and continuous random variables. So discrete are countable and continuous are not countable. We're going to identify discrete probability distributions and we're going to graph them using StatCrunch. We're going to calculate and interpret the mean of a discrete random variable. Interpret the mean of a discrete random variable as an expected value. That will be a big term. And the standard deviation of a discrete random variable. Again, a discrete is we are countable. So let's consider the probability experiment in which we flip a coin 2 times. So the outcomes are heads, 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 tails, tails, heads, tails, tails. So rather than being interested in a particular outcome, we might just be interested in the number of heads, for example. Okay, now if the outcome of a probability experiment is a numerical result, we say the outcome is a random variable. So a random variable is just a numerical result of the outcome of a probability experiment. So its value is determined by chance. Okay, and we typically will denote a random variable using a capital letter such as capital X. So when we're talking about a random variable, when you see those capital letters, that's what we're going to be looking at. But again, random variables, these values, these probabilities are determined by chance. So in our flipping of a coin example, if the random variable X represents the number of heads in 2 flips of a coin, there are some possibilities. You could have 0 heads, 1, or 2. Okay. So notice that we follow the practice of using capital letters such as capital X to identify that random variable, and lowercase x, or lowercase letters, to list the possible values of that random variable. So again, capital X up here, that was the random variable, is just the number of heads flipped, and then lowercase x represents the actual values that it can take on. Or you can think of it as a sample space of the experiment. Okay. Now, as another example, consider an experiment that measures the time between car or arrivals of cars at the drive-thru. This random variable, we'll call it capital T, describes the time between arrivals, so the sample space is t is greater than 0 because time is continuous. So we can't say 0 seconds, 1, 2, because if time, time doesn't round automatically to nice even numbers. It's always moving. It is continuous. So there are 2 types of these random variables, discrete and continuous. So a discrete random variable either has a finite or countable number of values. Okay, and they are discrete. That's why we use the word discrete. So the values of a discrete random variable can be plotted on a number line with space between each point. Okay, whereas continuous has infinitely many values, and they are plotted on a line. When we plot this on a line, it is an uninterrupted graph. There's no space between them. So in these questions, so question 6, let's determine whether the variable is, or the random variable is discrete or continuous, and in each case state the possible values. So the first one says the time it takes for a light bulb to burn out. Okay, again, whenever you see time, time is continuous. And so there's really nothing we can do about, there's no way time can be discrete for us. So it is a continuous variable, and time can be greater than or equal to 0. We can't have negative values in time. Okay, the weight of a T-bone steak. Now you may think, yeah, that's discrete because it can only weigh so much, but this is actually also a continuous variable where the weight must be greater than 0 because you have to have something. But the weight, you may look at something and you say, well, the scale says 2.3 pounds. Well, that's what the scale says, but the scale can only measure to so much precision. It could be 2.324579, whatever. It could have this never-ending decimal. So there's no way for us to exactly pinpoint, unless we're very limited on whatever type of scale we mean or use. The number of free throw attempts before the first shot is made, that is discrete, because we can count those free throw attempts. So in this case, x would be 1, 2, 3, and it would have no bound until you make the first shot. Okay, and the next one is simple random sample of 20 people. The number with type A blood. Okay, so this is discrete. Oops. Discrete. And you could have 0, you could have 1, you could have 2, all the way up to 20 in this one. Okay. So that's a look at the difference between a continuous and a discrete variable. And hopefully, again, just think discrete, you can count it. There's a way to count it out. There's a way to put some space between one variable or one outcome and the other, where it's continuous. It's not countable. So now we're going to talk about the idea of a probability distribution. And we will use different probability distributions in this class, but they're going to follow these same rules. So the probability distribution of a discrete random variable, capital X, provides the possible values of the random variable and their corresponding probabilities. Okay, so a probability distribution can be in the form of a graph, a table, or even a formula. Okay, so here are the rules. Let P of X denote the probability that the random variable X equals some lowercase number. So, if we were looking at the number of people type A blood in a group of 20, as we mentioned in the last one, say what's the probability that 5 of the 20? Then that X, this lowercase x, would be 5. So remember, in a probability distribution, the sum of all the probabilities has to add up to exactly 1, or 100%. And the probability of any individual outcome has to be between 0 and 1 inclusive. You can't have more than 1. You can't have negatives. It's got to be between 0 and 1 inclusive. Okay, so in these two questions, we want to determine whether the distribution is a discrete probability distribution, and if it's not, let's say why. So first, we're taking on discrete values 0, 1, 2, 3, 4, so we're good there. If you add up, so the sum of all of these, if I add those up, it does add up to 1, and notice that every probability here, all of these are between 0 and 1. And you could include 0 and 1, but they're all between 0 and 1, so yes, this guy is. Okay, number 11, it fails right here. You cannot have a negative. So we would say no, because the probability of getting 50 is equal to negative 0.15, which is less than 0. Can't have that. So automatically see that, we throw it out. Even if it adds up to 1, can't have negative values. Okay, now if we have a discrete random variable, then we can find the mean of the discrete random variable. And the mean of the discrete random variable is found using the formula. So the mean, mu of x, is the sum of the x value times its probability. So you add up every product. So if 1 has a probability of 0.2 and 2 has a probability of 0.3, whatever, you take 1 times 0.2 plus 2 times 0.3, and you would just sum all those up. Okay. Again, where x is the value of the random variable and p of x is the probability of observing that. So here's a small interpretation of the mean. So suppose an experiment is repeated n independent times, and the value of the random variable x is recorded. As the number of repetitions of the experiment increases, the mean of the n trials will approach the actual mean, the mean of the random variable. So in other words, If you let x1 be the value of the random variable x after the first experiment, then x2 is the value of it, our random variable x after the second experiment, and so on and so forth. Then x bar would be just add all of those together and divide by n, just finding our regular mean. And then if we were to look at, okay, so we just keep repeating this experiment over and over and over again, the difference between x bar and the actual mean will get closer to 0 as n increases. So that's what we're talking about when we're discussing the interpretation of the mean of a discrete random variable. Just the more we repeat the experiment, the closer we are going to get to the true mean. But the way we actually theoretically calculate the true mean is the sum of x times its probability. Okay, now the standard deviation is a little bit more difficult to calculate, but this discrete variable, or excuse me, a discrete random variable can have a standard deviation. Okay, sigma of x is the sum of the deviation squared times the probability of x. But a more used formula is this 2b formula, which is the sum, and we're taking the square root because we're the standard deviation, of x squared times the probability of x. So instead of x times p of x, we take x squared times p of x, and then we minus the mean from that. And that's going to be how we find the standard deviation. But we will we'll definitely cover an example here to get through this. But let's see, how much time do I got? So we'll get this one started, but I don't think we're going to finish it up. But so Ichiro, who was a baseball player, called his hit parade. In 2004 baseball season, Ichiro of the Seattle Mariners set the record for the most hits in a single season with a total of 262 hits. Okay, in the following probability distribution, the random variable x represents the number of hits he got in a game. So either 0, 1, 2, 3, 4, or 5. Okay, first we want to verify that it is a discrete probability distribution. Okay, so you take the sum of the probabilities, so add up all of these probabilities. It should equal 1, which is true. And notice that every probability is between 0 and 1 inclusive. That is, we can check the box on that as well. So it is a probability distribution, so we'll say yes on this. Okay. Next, we want to draw a graph of the probability distribution, describe the shape. So when we are drawing this, we are going to be using StatCrunch, so I don't expect you to draw this on your own. So I'm going to jump over to StatCrunch. I do need to input my data, and then we'll come back. Okay, so now I've got my my variables and their corresponding probabilities. So the way we're going to get this graph is going to go to Stat. Under Calculators, you're going to drop all the way down to Custom. And in a Custom, it wants to know what are the values. So our values are these 0, 1 through 5, so that's the X column. Then what's the weight, or in this case the probability, so that's in the P of X column. And we compute, and we can now see here is the distribution. Notice the space between because we are discrete. It's either 0, 1, 2, 3, 4, or 5. Okay, so that's going to be the how we come up with the actual graph that we are looking at. Notice it does spit out the mean and the standard deviation for you as well, which is nice and convenient. But we are going to go through and find those on our own using those formulas so we can get an understanding of those. But for now, we'll just wrap up part 1 here with this. Again, StatCrunch is going to be a huge help for you, so make sure you understand and are able to produce this graph.